Welcome to everybody watching this video. Today I'm going to talk about some work that I've done with Rink Hoekstra at the University of Groningen about whether scientists can use significance testing logic while doing a simulated experimental task. I probably don't need to tell you that there's currently a debate about the role of statistical methods in what is often called the replication crisis. In particular, both the core logic of significance testing and people's understanding, or rather misunderstandings, of significance testing have been blamed for various poor practices and unexpected failures to replicate. For decades, misinterpretations of significance testing have led to calls to abandon significance testing altogether. There are two main lines of evidence that are cited to support researchers' misunderstanding of significance testing. The first is from statistical cognition experiments. In these studies, participants are often given a research vignette and asked about their interpretation of some related statistical result. People often misinterpret these statistical results. For instance, in a famous study by Oakes in 1986, almost every researcher asked to interpret a p-value misinterpreted it in various ways. However, this kind of evidence has a number of weaknesses. In particular, it may not always be clear to the participant what is being asked in a vignette study. Moreover, it is important to separate a common representation of the results of a significance test, that is, a p-value, from the logic itself. Misunderstanding a technical term does not necessarily mean you find the underlying logic difficult. Finally, by their nature, vignette studies are passive in the sense that the research result is simply given to the researcher. Researchers did not generate it as a part of some search for truth, and thus we cannot assess their ability to use significance testing to find the truth. A second line of evidence for researchers' misunderstanding of significance testing is misuse and misinterpretation of significance tests in actual research results. These may not always be driven by actual misunderstandings. Rather, they may be the result of incentives for cutting corners in statistical analysis or even just careless writing. We used a novel statistical reasoning task to study researchers' use of significance testing logic. We boil significance testing down to its bare bones, in which observed results are compared to those expected under some null hypothesis. Extreme results relative to what was expected are taken to contradict the hypothesis. Importantly, we wanted to disallow other ways of coming to a correct answer. We prevented participants from using common heuristics and other statistical reasoning strategies such as confidence intervals, likelihoodist, or Bayesian statistics. We did this by making use of a feature unique to significance tests, that evidence is only in relation to a null hypothesis and that a p-value can be computed from any monotone transformation of the test statistic. What this means is that we do not need to give participants any numbers at all. We just need to allow them to sample from a null distribution, which they can compare to their observed experimental results. We intentionally left participants in the dark about the numerical value of the sample size and test statistic. They only had an indication of when these numbers were bigger or smaller. In this task, participants were only given statistical results on a numberless interface. The x and y coordinates gave them ordinal information about the statistical evidence and the sample size respectively. The cover story was a two-sample design. Participants were required to determine whether one team of Christmas elves, sparklies on the left or jinglies on the right, were faster at making toys than the other team. When they requested the results of a fictional experiment, the result was delayed in proportion to the sample size, inducing a resource trade-off. After a delay, the result of a fictional experiment was displayed on the interface as a point. Participants could manipulate the sample size at will. If desired, participants could also sample from so-called random shuffle reports, which were fictional experiments in which jinglies and sparklies were randomly assigned to two teams, ensuring the null hypothesis is true. These null samples took no time to return. Participants could perform the task as long as they liked, at the end responding whether they thought jinglies were faster, sparklies were faster, that they couldn't determine which, or that the teams were the same. Participants were randomly assigned to a combination of conditions, including whether the truly faster team was the sparklies or jinglies, and the size of the true effect in standardized units, which ranged from 0 to 1. There was a third special manipulation. We randomly assigned each participant to one of two transformations of the test statistic. This had the effect of visually stretching out all of the distributions for some participants, but statistically, the conditions were exactly the same. If our participants can use significance testing logic effectively, we expect them to be able to identify the correct answer with a low false positive rate for those participants who are assigned to a null effect size. We also expect performance to be sensitive to the strength of the signal in the stimulus, that is, the true effect size. Finally, if they properly compare to the null distribution, we expect them not to be sensitive to the irrelevant visual width manipulation. To give you a sense of how the visual width manipulation worked, I'm showing two hypothetical sequences of fictional experiments that differ only by their assigned width. To aid understanding, I've plotted the equivalent two-tailed p-values from the null distribution on the display as vertical lines with labels. The participant would not have seen these. They would have had to discover them through repeated sampling. The top display shows samples from the narrow width condition, and the bottom shows samples from the wide condition. A competent participant can perform the task in two ways, by comparing to the null distribution, or by counting observations left or right of center and comparing to a null of half left, half right. Both are valid significance testing strategies, though the latter throws away information. We recruited participants using social media such as Facebook and Twitter and by email. We excluded participants who were not scientists or trainees, who did not have some training at the university level, and who did not follow directions. After exclusions, we were left with 506 participants. Here, I'm showing the proportion of various responses as a function of the true effect size. On the left, the correct answer was sparklies. On the right, jinglies, and in the middle, for an effect size of 0, participants should have either said that they could not detect which team was faster or said that they were the same. The points show the observed proportions. The lines show expected proportions from a simple signal detection model fit, and the shaded bands around the line show approximate standard errors around that line. The inverted V-shaped line shows proportion of no detect and same speed responses as a function of effect size. At 0, about 85% of participants declined to pick a faster team, meaning that the false positive rate was about 15%. Although this is higher than the typical 5% used for scientific purposes, this is just a game to the participants, and we did not ask them explicitly to be conservative. In this context, a 15% false positive rate is less alarming. There's nothing special about 5%, of course. Importantly, the participants' responses show a strong sensitivity to the true effect size. Their ability to identify the correct answer rises quickly with the true effect size, and only 2 participants out of a possible 370 make a sign error. Next, I'll show the effect of the visual width manipulation. On the graph, along the x-axis will be the visual distance from the center of the most extreme fictional experiment that the participants sampled. Within each group, this is a salient index of the statistical evidence, but this visual extremeness has a different interpretation within each visual width manipulation condition. On the y-axis, I'll show the predicted probability of responding jinglies or sparklies, that is, that the groups are different, from a logistic regression fit. We would expect there to be a strong relationship between the visually most extreme point and the probability of responding that the groups are different. At the top and bottom of the graph, I'll show the individual data points so you can see for each participant how extreme their most extreme point was and whether they responded that the groups were different or not. At the top, I'll show the data points from the narrow condition, and at the bottom, I'll show the wide condition. First, the narrow condition. As you can see from the data points and the logistic regression fit, there is a strong relationship between the extremeness of the most extreme point that they observed and the probability of indicating a difference between the groups. When the participants saw extreme points, they were more likely to respond either jinglies or sparklies. When they did not, they were more likely not to. I've also marked the implied two-tailed 5% distance from the narrow null distribution. Participants whose most extreme point was as extreme as this had about a 20% probability of indicating that there was a difference. I've now added the wide condition to the same graph. As would be expected if participants were using the null distribution to calibrate, the participants in the wide condition discount the distance more. I've marked the implied 5% two-tailed distance from the wide condition. Participants whose most extreme point is as extreme as this have again about a 20% probability of indicating that there is a difference. However, for the same visual distance, about 75% of participants in the narrow condition would be expected to indicate that there is a difference. Participants appear to be successfully calibrating to their null distribution. We don't have to just guess at how the participants perform the task. We also ask them to describe their strategies with 3 open-ended questions. We were actually surprised and pleased at how many participants were willing to spend time detailing their strategy. We coded the responses as either reflecting strong significance testing strategies, where the results were compared to null distributions or some notion of sampling variability, or weak strategies, such as using the sign of the effect or asymmetry. These strategies are weak because they throw away information, but they may be heuristically easier. Here, you can see examples of responses coded as strong and weak. The participant with the strong response is indicating that responses could be quite visually extreme even when sampling from the random shuffle reports, the null distribution. Thus, they correctly discount experiments that show that level of evidence. The participant who gave the weak strategy response is considering only the asymmetry and did not mention any notion of using the null samples. Finally, some participants gave no relevant strategy response, though a few continued the cover story in entertaining ways. As you can see in the graph, the overwhelming majority of participants were coded as indicating some strong strategy. We must be cautious, however, because this may reflect the task instructions or the participant's statistical training. They may not have any other words to describe statistical reasoning. However, many of the responses were lucid descriptions of significance testing logic applied to this novel task. This would be surprising if they did not understand significance testing. Furthermore, combined with the fact that the participants' responses appear to indicate success in applying significance testing logic, we believe these results provide strong evidence that scientists can reason using significance testing. We believe these results provide reason to doubt the status quo opinion that scientists find significance testing reasoning backward or difficult. Our participants were given an opportunity to show statistical competence by finding a correct answer in a kind of novel puzzle, and they succeeded. If scientists can use significance testing reasoning, reform efforts to eliminate significance testing may be ineffective or even cause unintended harm. A demonstration of the task, draft manuscript, supplement, materials, data, analysis code, and more are open and freely available at the location shown here. Thank you for watching.